Okay, what I've got here is a combined power cycle where I've got air, Brayton cycle, turbine, gas power cycle up here, and then I've got a vapor power cycle with water down here. Okay, so the temperature, I can get air is much higher than I can get water. So instead of just dumping air back in, I'm going to use that heat to heat up the water, put it through a turbine, and do it that way. So I only have, for the total system, I only have one Q in, one Q out, although I have two systems where Q out of one is Q into the other. Okay, and up here I've got all my H values for each of the states given here. So, typically that's what we would start doing. This time it's given to me, so things are going to be pretty good. Okay, what I know is this Q in is 50 megawatts. Okay, so I'm going to use that to find the mass flow rate. So I'll start by finding the mass flow rate of the gas turbine, the gas power cycle right here, because I know the heat transfer into that. So again, I know Q in equals mass flow of the gas cycle, and again, that'll be basically H3 minus H2. And again, from this, I know Q in, I know H3, I know H2. The only thing I don't know is the mass flow rate of the gas cycle, which is going to be 51.4 kilograms per second. Okay. Then once I have that, I can use what's going on here to help me find the mass flow rate of the vapor power cycle, which is to say, remember, Q out of this one is Q into this one. So what I have is the mass flow rate of the gas times H4 minus H3. That is Q out of the gas power cycle. And again, that's going to equal Q in to my vapor power cycle, which is going to be then H7 minus H6. And again, because I've found all my H values, this becomes pretty straightforward. I found my mass flow rate of the gas. And then knowing Q out is Q in of that, I can from this find the mass flow rate of the vapor power cycle to be 7.34 kilograms per second. One more mass flow I need to find is the cooling water. Again, same idea here. Q out of my vapor power cycle, which I just found the mass flow of now, which is going to be H8 minus H9, equals the mass flow rate of my cooling water, which is going to be H11 minus H10. Again, Q out of my vapor is Q into the cooling water. So I just take the mass flow delta H of each of them, set them equal to one another. The only thing I don't know here is the mass flow rate of the cooling water, which I find to be 232.2 kilograms per second. And again, I can find all of this because I have all of my H values. That would always be the first thing to do in this problem. They're all given to us. Okay, so those are all my mass flow rates. Now that I have those, I can find the net power, which is going to be, the turbine minus the compressor of the gas turbine, turbine minus pump of the vapor cycle. Okay, so the net power, the work of the cycle, is going to be the mass flow rate of the gas times, again, the turbine minus the pump, which is going to be H3 minus H4 minus H2 minus H1. So that's the work of the gas power cycle. Now the vapor power cycle is going to be the mass flow rate of the vapor times its turbine, which is going to be H7 minus H8 minus its pump, which is going to be H6 minus H9. So again, once I have all my mass flows, I have all my H values, it's just turbine minus compressor, turbine minus pump. That'll give me the total work of the cycle, which is going to be 23.66 megawatts. Okay, where specifically the gas power cycle is putting out 17.9, and the vapor power cycle is putting out 8.47. Okay. Regardless, once I have that, now I can find the thermal efficiency, where the thermal efficiency is that work of the cycle I just calculated all over Q in, which was given to me. And this, again, is my only Q in. And that gives me a total thermal efficiency of 52.7%. And again, that's quite a bit more than we would typically get, say, from vapor power cycle. And the idea is we use as much of that heat as possible. Rather than just dumping this heat back into the atmosphere, I use the hot gases coming out of the turbine to heat some vapor up to put through a turbine and get a little bit more performance out of it. Okay, so that's the idea behind a compound. It's two cycles where Q out of one is Q into the other.